We are doing the second page of your notes from yesterday. We have these two concepts that I want to quickly go through. So, number one, you have got two ways to find the equation of the line so far. One way is if you have been given a table such as this, you know that you're going to go into your calculator, put those into your list, and then how do you compute the equation of the line? Okay. Stat Cal Linreg number 8. Very good. The other way that we learned yesterday how to compute the equation of the line is how to read a computer printout. Okay? So we're going to use a computer printout, and then we're going to be able to find that equation of the line. All right. Next, the third way that we're going to learn how to do an equation of the line is what we're going to learn today, because you could be given different information. Specifically, the type of information you may be given is correlation coefficient, the standard deviation of the x values of the points, and the standard deviation of the y values of the points. These three items are used to find the slope. So the slope. Now, in your other classes, algebra, just plain functions, how do you find the slope? Yeah, the difference in your y's over the difference in your x's. Well, there's a somewhat same relationship here. It's the variation in the y's over the variations in the x's, but I also have to relate it to how well correlated the data is. So that then gets multiplied by the correlation coefficient. Okay? So that is how you get your slope, given those three items. Next, we need to have a point that is located on the line. And the point on the line that we know that we could always count on being on the line is this thing called the mean point. And so let me tell you what the mean point means. It is the mean of the x. So if you take the average of the x data and you take the average of the y data, then you have a coordinate x bar, comma, y bar. And that will always be a point on the least squares regression line. So if you have your data and you have your least squares regression line, then you can count that the mean point is always going to be a point on that line. Therefore, you have a slope, you have a point, you then use your algebra skills to get the equation of the line. Let's do that now. Here we go. Becky's parents have kept records of her height since she was born. The data consists of Becky's age in months, and then her heights in centimeters, and so here are the data statistics. My first question is, what item do you think is the explanatory variable? What would be explaining in this case?
Age.
I agree. Age in months would be your explanatory, and then the height would be the response to that. So, this mean age would be represented by your x bar, because that is the average of the x variable. Mean height would be your y bar. Over here, standard deviation of the age is s of x, and then this is s of y. Additionally, we are told that the correlation between age and height is 0.86, so that is your correlation coefficient. So, we want to find the equation of that least squares regression line. First step, find the slope. Correlation times variation in y over variation in x. And fill in the numbers. That does multiply out to 0.415. Okay, so we have that. We also know that the point on the line is 44,82. How can we then, we need the y-intercept. How can we get the y-intercept? We do. Good. He's describing using the y equals mx plus b And we're using that with the point on the line that we know is on it. So out of these four items in this equation, we know that the mean of y is 82. And we know that the slope is 0.415 because we just found it. And we know that the mean of x is 44. So then you solve for b. Do that now. Okay, so I did the math. You might want to check this on yourself to make sure you're doing the actual steps correctly. If you feel a little weak in that area, 63.74. So we write our equation as predicted height in centimeters equals. I want you to go ahead and keep that format from Lynn-Reg number 8, which is the y-intercept first. This will help us in chapter 10, plus your slope times your x value, which is age in months. Okay, done. So there we go. There is the equation of the line given those various items. It's pure just kind of plug and chugging your values. I want to give you a moment here to do this one. We'll check that, and then we'll go to the next page. A small little thing to learn on that page. So do this problem now. Okay, so since you don't have context, then you are just leaving in terms of x's and y's. And so here's your answer. Okay, so any questions on that? Okay, good. So you had that process. Good. Now, on this next page, I absolutely realize that the best way to do this problem is pure calculator, where you put your data into L1, L2, and so on and so forth. I'm going to have you actually do this the way we did on the previous page for practicing purposes. Okay? Just for practicing purposes. And I'm going to teach you about this new thing in your calculator called two-variable stats. So, if we are going to do this problem like we did on the previous page, we need 5 pieces of information. What are those things we need? Standard deviation of x and standard deviation of y. Very good. Okay, so you told me these are all the things that I need, and I'm going to show you and tell you that you can get all these pieces of data from your calculator using this two-variable stats. So I'm going to teach you how to do that. Put your data for this into your L1 and L2. While you're doing that, let's talk about what you think the response and explanatory variables should be. This is the National Institute of Health study, and it's referencing the number of cigarettes smoked a day and the birth weight of the babies. So what of those two variables do you think would be the X variable, the explanatory? Okay, good. That number of cigarettes, and then the response would be the birth weight. Okay, so now that you have this data in your calculator, we want to compute the two-variable stats. That's going to do, so let's go to stat over to calc. And let's look at this menu. We've done several things in this menu. Number one, we used when we just had one variable. And we were getting the information, say, for the 5-number summary for our box plots, or it also gave us standard deviation and mean and all that kind of stuff. Well, two-variable stats is basically going to do the same thing, but 2 at a time. Okay, so if I go to two-variable stats and I hit enter, it's going to default to L1 as the X values and L2 as the Y values. So if you have your data somewhere else, you would have to command it differently. For example, if I had my data in L3 and L4, I might say, okay, I have my X data in L3 and my Y data in, I don't know, let's say it's in L6. So wherever you have your data, you could command it to compute that. But Since you guys have your data in L1 and L2, it defaults to that, and when you calculate it, let me show you what all it gives you. This top value is x bar, so that is going to be the mean of all your x's. And if you look down a little bit, you get the standard deviation of the x's at 8.26. So let's write those in at 18.17 and 8.26 as the x information. If you arrow down, then the y information appears. And I have the mean of the y is 5.95. And look a little further, the standard deviation of the y's is 1.01. So I'm going to fill those in. Now, the weird thing is it does not give you the correlation between those two. So I absolutely understand this is really just kind of an asinine step, just kind of ridiculous. You actually can only get that correlation through the linear regression. So if you stack out lin reg number 8, of course it's going to show you the equation components. It also tells you that the R value is negative 0.95. Now, my intent would be then for you to practice this process again, getting your slope and plugging it in and all that kind of stuff. But if you did that, you could see that you would be getting that the birth weight, the predicted birth weight, comes out to be 8.06 minus 0.116 times the number of cigarettes per day. Okay. Yes. Yeah, I had to get that from my stack calculin reg. I had to calculate the linear regression and make sure your diagnostics are on. Okay, yeah, and I absolutely understand. I mean, you're saying, okay, the line steps right there. Yes, but I'm just having you practice this other process. Okay, I don't think that we need to do number 4. I'm going to give you the answer so that if you feel that you need an extra practice, it would be this percent increase in sales is 2.15 plus 0.466 times the percent increase in advertisement. Okay, so the last item. Yes, this is really actually a very poor chicken scratch stuff. Let me tell you what happened is that a few years ago, there's this rule that you have to know about what kind of things affect the correlation coefficient. So the question is, what items affect the correlation coefficient? And so, it was told to me just as a rule, nothing does, unless you're going to be multiplying by a negative. So I don't really like that answer. So, because I like to know why. I don't appreciate just being told, here's a fact you got to know, here's the way it is. I want to know why so that it sticks and I remember it. So, let's go through these facts about the correlation coefficient, and then I want to run a little bit through the kind of proving of it to you so that hopefully this will stick in your brain. So, here we go. Number 1, would you say that the correlation coefficient is the thing that measures the strength of the linear relationship between those items? Is that what correlation coefficient is doing? Yes. It's referencing, it's clustering around a line. Good. Would you say that the R value is affected by outliers? Let's think about that. This correlation here, what would you consider this? Is this going to be relatively strong or weak or what? Good. That's going to be relatively strong because I have a nice, tight cluster around the line. However, if I had an outlier introduced into the data, then that is kind of pulling away from the tight cluster around this line. Correlation to. So, what would happen to the R value? The R value actually does what? It becomes weaker. Now, numerically, what happens to it? It becomes a smaller strength and closer to 0. Okay, it's going to be closer to 0. All right, this next one is that the correlation coefficient ignores the distinction between response and explanatory. In other words, you can switch the x and the y values and the correlation does not change. Okay? Well, I pretty much was like, I don't get that. Quote unquote, prove it to me. Tell me why. I don't like you just saying that. That's weird. So, this was kind of some chicken scratch I had put down, and then I thought I probably need to show stuff better, so I rewrote that here. Let me explain. This is actually the equation, which thankfully we do not compute on our own, because this is basically you have to get the z-score for every x direction piece of data and the z-score for every y piece of data. You're multiplying and you're getting that product. You're summing it up and then getting that average distance. Okay? Thankfully, we are not ever expected to know how to do that by hand. And guess what? Because of this thing you learned about a long time ago, the commutative property of multiplication. A real simple example of that, 4 times 3 is going to be the same as 3 times 4. Well, guess what? This value times this value will be the same because of the commutative property of multiplication. That product will be the same. So, switching your x and y values will not change the strength of your correlation. Okay, so that's something that you need to know. Furthermore, R is not affected by changes in the units. And what I mean by that is not only multiplication and division. For example, if you were going from feet to inches, something along those lines, that's going to need multiplication or division depending on which way you're going on that. Multiplication and division, also addition and subtraction. Because for addition and subtraction, think about this. I take this correlation and I scoot it this way. The correlation, the way that they are correlated around the line, does not change if they had all moved. Okay? It's just shifted. So adding is not changing the correlation around that line. Furthermore, this thing right here, whenever I multiply it, it is also still proportionately related to the line. And since this formula is built off of this proportion relationship here, it doesn't change. So, in summary, transformations do not affect your correlation. The only exception is if you multiply one variable by a negative, that would change a positive correlation. How will it never just take the whole thing? Okay, so that would take this positive correlation and it would make it rotate and then just be negative. Okay? Okay? So, multiplying one of the variables by a negative would just change it to the same correlation, but in the opposite direction. So the sign would change, and that's it. Okay? So there we go. That is about the correlation not changing with transformations. Done. Now I want you to work on, in class, your assignment, because it's quite lengthy,